Hello everyone. So for today's lesson, we are going to be talking about the thin lens equation. And so the thin lens equation is basically the mathematics of optics. Now, what we've been doing in optics so far has been drawing ray diagrams in order to find the image. And so the image, by finding the image, we're able to, find a lot of qualitative properties about the image. However, we may want to know quantitative properties about the image. And that's exactly what the thin lens equation allows us to do. It's worthwhile to note that this equation can also be used on mirrors. So here's the equation. It's 1 over f is equal to 1 over di plus 1 over do. Okay, so that's the equation. Now, I want you to pause the video and think, what do you think f stands for? So, I don't know, hopefully you've paused it and figured it out. F is going to be the focal length. Di is going to be the distance of the image. And do is going to be, pause the video if you want to, it's going to be the distance of the object. So what I've done here is I have drawn my basic lens ray diagram starting point, and I have a converging lens. So I'm gonna stick in an object. You know what? We'll put the object right there. And if I go ahead and do my little rules, we've got parallel, stop at that vertical line, through focal. We've got V to V, and we have focal through parallel, and I can draw my object. Now, of course, I could state my salt here, which is size is the same, attitude is upside down, location is on to F, and type is real. But again, that gives us qualitative information about the image. I want some quantitative. Let's talk about some of those variables. So the first one is the focal distance. I should clarify distance. And when we're talking about distance, we are referring to the distance between the point of interest and that vertical axis through the middle. So when we're talking about focal distance, we would be talking about this distance right here. So we're going from the focal point to that vertical y-axis. We could also use this focal point as a distance because it would be the same distance. So either one works. And that is going to be the F. Next, we have the image distance. So we're going to go from the image over here. And so the image is over here, and that will be from the image to that vertical distance. So that's di. And finally, we have our distance of the object. And that distance will be right here. So that's di. Now, when using this equation, you will often be given a word problem, and you will be given 2 of the 3 pieces of information you know, or you might be given enough information to be able to just figure it out. So you might see a variety of different things. Let's go over the most basic. Let's say, in this case, the focal distance is going to be, 6. So f is equal to 6. So in a word question, it would say the focal distance of a converging lens is 6. And then the distance of the object, di, is going to be 12. And you know, usually there will be units. So let's just say centimeters. At this point, I am able to pull down my equation, which is 1 over f is equal to 1 over di plus 1 over do. And of course, the unknown here is going to be distance of the object, so distance of the image, my apologies. So we're looking for di. What we can do now is go ahead and fill in my known variables. So this is 6, oh bother. 6 is equal to 1 over di. We don't know what that is, so I'm just going to leave it as di for now. And that will be plus 1 over 12 for distance of the object. And this is where we have to get a little mathy. Now, if you're comfortable with algebra, you should have no problem at all. And I would encourage you to pause the video and see if you can figure it out. If you are not comfortable with algebra, then keep watching and we'll do it slowly. So what we have to do is isolate our variable. Our variable of question in this case is this right here. So I need to get that by itself. What that means is I need to take this and put it over here. Now I can't just pick up a number and move it. That angers the math gods, and we don't like to anger the math gods. So in order to sort of get rid of it, I need to do the opposite mathematical function. In this case, right now, we have a positive. So the opposite function to that is going to be a negative. So 1 over 6 is equal to 1 over di plus 1 over 12. And I have to do the negative minus 1 over 12 because 1 over 12 minus 1 over 12 is 0. So that cancels that out. Now, when I do something to one side, again, that breaks the laws of math, it angers the math gods. So in order to appease the math gods, what I do is I do the same thing on the other side. So actually what I'm going to do is I'm going to rewrite this 1 over 6. So I'm just moving that to give me a little space. And I'm going to do the same thing on the other side, which is to put in a minus 12. So this is repeated over here. So that's some basic algebra, but I'm going slowly just in case you need this refresher. What I am left with is 1 over 6 minus 1 over 12 is equal to 1 over di. So that's great. I have di almost isolated. It's not quite done yet, but we'll get to it. So at this point in time, I need to simplify this equation. And to simplify this equation, I need to first subtract these two fractions. If you recall grade, 5 or 6 math, in order, actually maybe 7, 8, in order to add or subtract fractions, they need to have the same denominator. In order to do that, you can play around with multiplying them, basically. So here, the easiest thing you can do is multiply this one by 2, because 6 times 2 is going to give us 12. But again, we don't want to anger the math gods, so whatever we do on the bottom, we have to do on top. So 1 times 2 is going to be 2. And this ratio has not changed in the slightest. So it's okay that I don't do that multiplication thing to everything. The ratio has stayed constant. Now that they're the same, I can simply subtract one from the other. So 2 minus 1 becomes 1, and nothing happens to the 12s. They're going to stay as 12. And simplifying that is equal to 1 over di. Now, here's another trick I wanted to show you as far as fractions go. For this case, it was really easy because 6 and 12 are multiples of one another. However, let's say we have a bunch of prime numbers, or just generally numbers that don't have multiples of one another. So, I don't know, let's go with 2 minus 1 over 7. Okay, so they're not multiples of one another. What you can do is multiply them by each other. So what this looks like is I would multiply this by 2 and multiply this by 7. Oops, I draw 3. So 1 times 7 is 7, 7 times 2 is 14, minus 1 times 2 is 2, 7 times 2 is 14, and so now we have them over top of the same denominator again. So if you're working with challenging numbers, this will give us, like this is another method that's fine. If you want to work with the multiples and just finding the sort of fewest steps to do it in, then this is a way that works. So this is foolproof. You can always do this method where you're just multiplying it by the other denominator, but whatever works. So here we have 1 over 12 is equal to 1 over di. Di is not yet isolated. We still have to do that. So I'm going to show you the long way first in order to isolate it. So to isolate it, depending on how comfortable you are with math, it can take many steps or few steps. So I'm going to do it the way that my brain works. Right now, it is being divided by that 1. So I'm going to do the opposite operation, which is to multiply it. And so that's going to get it to be over there, and that will cancel it out. What I do on one side, I have to do on the other side, so di times that. And so what we're left with is di over 12 is equal to 1, because di times 1 is just going to be di. And now di is still not isolated, so I'm going to do the exact same thing. I'm going to multiply this by 12 to get rid of that, multiply this by 12, so that cancels out, leaving us with di is equal to 1 times 12, which is 12. That's the longer version of it. I can also show you this version. So we were left with 1 over 12 up here is equal to 1 over di. This is the shortcut. So this is what's called cross multiplication. It's effectively the same thing, but it is fewer steps, sort of. So what I'm going to do is I'm going to take 1 and cross multiply it with di. So that becomes 1 times di. And I'm going to do the same thing over here. So that becomes 12 times 1. Now, you'll notice 12 times 1 is 12. 1 times di is still di. So whichever method you take, the slower step-by-step version, or if you're going to cross-multiply it, you're still going to get 12. And don't forget units. We were working with centimeters. Now, here is the key. You need to go back up and check your work. So we have 12 centimeters for the distance of the object. Looking at this image, you want to double check that it makes sense. Now, the value we had for di was 12 centimeters. And in fact, it does make sense, because if this is 12 centimeters over here, oh, sugar. This should be do, my mistake. So this should be 12 centimeters. And notice it's on 2f, and 2f is double the length of the focal length, which is 6. So 6 times 2 is 12. The distance of the image is also on 2f, and so it makes sense that this is going to be 12 centimeters. It doesn't always end up that way, depending on where the object is. So there are also some sign conventions that we need to discuss. Conventions. Which means positive or negative in terms of answers. So if it's a converging lens or double convex lens, then F is going to be positive. So that's this case right now. F was positive, so our example was 6 centimeters. If it is a diverging lens, then F will be negative. So it could have been, for example, negative 6 centimeters. In this case, the distance of our image was positive, and that indicates whether the image is real or virtual. In this case, it was real. So if it's on this side, or the opposite side, I should say, the image is going to be real, and therefore the distance of the image is going to be positive. And of course, the opposite is going to be true. If the distance of the image is negative, then it indicates that it's a virtual image. This is how I remember it. If we are looking at a lens and we have this sort of standard setup where we have our, zoom out a little, we have our lens and we have our object over here. Anything on the opposite side is going to be positive. Anything on the close side is going to be negative. In terms of focal point, at least in my mind, I think of this as the main focal point for a converging lens. And this one over here is sort of the main focal point for a diverging lens. In my mind, okay, that's how I remember it. And so the focal point over here is positive because it's on the opposite side. The focal point over here is negative because it's on the near side. If the image is over here, then it's going to be positive. If the image is over here, then it's going to be negative. Okay, what I want you to do is a practice problem. You are going to use the thin lens equation. 1 over F is equal to 1 over di plus do, 1 over do. And the variables we're working with is do is equal to 8.3 centimeters, and F is equal to 15.2 centimeters. Let me tidy that up a little bit. 15.2. The first thing you should do is draw it out. So draw a ray diagram. This will help you to figure out what is the answer that you should get. Because the focal length is positive, that indicates to me that we're using a converging lens. And you don't have to draw the exact distances, you just have to approximate. So here's our focal length, and our distance of F is going to be 15. So F is equal to 15.2. And our object is only going to be 8 centimeters away. So it's actually going to be closer. Let's just approximate here. So our DO is 8.3. If we were to draw a ray diagram, then we should be able to figure out where our image will be. So I encourage you to pause the video, do this on your own, and figure it out. That way you can predict it. So draw it out and see if you can predict the answer. I didn't press play, so I'm redoing all of this. What I want you to do now that you've drawn it out, predicted where you would find the image, go ahead and plug those numbers into the calculation and see if you can do it on your own. check your answer with mine. I'm going to go ahead and do my answer, so make sure to pause the video. Shoot. So I'm just going to take the formula and put my answers in. So 1 over f, where f is 15.2, is equal to 1 over do, or di, I guess, is what we were trying to find, plus 1 over do, where do is 8.3. Just to simplify things, I'm going to jump through this math part a little bit more by doing that opposite function over here, 8.3. So I'm just moving that 8.3 over di. And you will get to a point where you can do that as well. I encourage you to take the long route while you're still practicing. That way, you know you're not making any mistakes. I'm going to be lazy or smart, depending on how you think about it, and just multiply these by each other, because who knows if there's any common multiple here. This is the easiest way to do it. And as I've already done this math, I know that 15.2 times 8.3 is 126.16. Do not round until the last step. And we have 15.2 over 126.16 to 1 over di. So 8.3 minus 15.2 is negative 6.9 over 126.16 is equal to 1 over di. Now what I can do is just cross multiply. So that leaves us with negative 6.9 times di, 126.16 times 1. So I could add that 1 in there if I wanted, but I don't care that much. Now di is still not isolated, so I'm going to isolate it by doing the opposite function of the number that's attached to it. Appease the math gods by doing it to both sides. That cancels out, leaving us with 126.16 divided by negative 6.9, which is 18.28. And since we started with 1 decimal, we should probably round up, making it 18.3 centimeters. Oh, and sorry, that was a negative there. So check your answer with mine. Did you get the same answer? Now, let's go up to our drawing and check that out. Okay, so if we draw in our little rules, oh sugar, that's the wrong one. We draw in our little rules here, parallel to focal, and then we have V to V, and we have focal to parallel. Make sure to draw your little arrows in. If we dot back our, oops, that's the wrong line. Always make sure to do the reflected ray. If we dot back our rays, or refracted rays, sorry, dot those back, and dot that back, then we come to an image that is about here. If the focal length is 15.2 from our problem, then our image distance is going to be negative 0.3, which makes sense because it's on the same side as the object, and it is a bigger number than the focal length. So it is always good to draw it out to help you confirm that the number makes sense. Okay, so that is it for our thin lens equation, just to review, we learned a new equation, 1 over f is equal to 1 over di plus 1 over do. We learned some what those letters mean, where f is the focal distance, di is the image of the distance of the image, and do is the distance of the object. And we learned how these numbers have meaning on our ray diagrams. So they don't stand separate. They only add to the information that we already have. And we can use both of them to find out information about our diagrams and our images and different things like that, which is important in a real life setting so that we can calculate some of the different variables. And by calculating those different variables, we can apply them towards different tech pieces that you either have already seen in class or will look at. Like any math problem, this requires practice. So be sure to ask for extra practice problems and ask for help if you need it. Good luck!